Hello guys, welcome to the part 2 of conduction. We're going to use mathematics. We're going to do heat transfer equation derivations. At the end of this lesson, you are expected to achieve the following two outcomes. The first is you should be able to explain the concept of thermal equilibrium, steady state, and transient. So you should be able to explain the meaning of each of these terms, their relationships, and includes the differences between them. And with this fundamental knowledge, then you can proceed to achieve the second outcome, that is to derive equations for heat transfer rate Qx and temperature profile Tx for different cases. So for your information, our syllabus cover 5 different scenarios. There are 5 scenarios which you are required to derive equations for. Watching this video, I believe you have already gone through activity 1-2. You have already gone through these 2 videos. Then the whole group has already come up with the mind map. So all this activity in group activity 1-2 are actually for achieving outcome number 1. So now I would like to invite you to enter this topic of equation derivations with the knowledge and understanding that you have gained so far, so that we can all together achieve outcome number 2. So you are required to derive equations for 2 properties. The first is heat transfer rate, Qx. The second is temperature profile, Tx, under 5 different scenarios. Scenario number 1 and 2 are basically similar. They are Cartesian coordinate, okay, x, y, z. Okay, one is with heat generation, another one is without heat generation. Scenario number 3 similar to 1. Okay, just that now instead of one layer, we have multiple layers. Scenario number 4 is no longer Cartesian system, but is for cylindrical system, and scenario number 5 is for spherical system. Okay, and so for heat transfer rate, because when you want to derive equations, we need to start from basic equation. Okay, so I want you to bear in mind, okay, in order to derive equations for heat transfer rate for Qx, so we always start from Fourier's law. I explained already in the last video, okay, on Fourier's law. Then in order to derive equation for temperature profile Tx, so we always start from energy balance equation, and this one I believe we have already learned in energy balance. Now firstly, let's take a closer look on Fourier's law. So Fourier's law states that the time rate of heat transfer through a material is proportional to the negative gradient in the temperature and to the area at right angles to that gradient. So basically we have already gone through the meaning of each symbol in Fourier's law. So if you still remember, so if you want to put Fourier's law in the form of rate equals to driving force divided by resistance, then the K will be here. Okay, I believe you still remember. Okay, so let's relate this formula to this system. So you can see it says that, so this is a system with irregular shape. So you can see the shape is irregular. So that's why you can see the A changes with X. So we see our boundary. Okay, the boundary is from X equals to X naught to X equals to X1. Okay, so you can see when X changes, A also changes. Yeah, so that's why when you derive equation, this A should be in terms of X. Okay, so then you put your X here, then you need to use calculus. So you can see Fourier's law is in the form of differential equation. So in order to solve this, in order to get Q, okay, to get Q, then we need to solve this equation, differential equation. Okay, using calculus, you need to use recall back all the calculus knowledge you have learned in engineering mathematics. Okay, so so you can see here within the boundary. So at X equals to X naught, we have the T equals to T naught, or sometimes we use T1. Okay, and when X equals to X1, then T equals to T1, or sometimes we put it as here is T equals to T1, here is equals to T2, here is X1, here is X2. Okay, it doesn't matter. So what we want to do is we want to solve Fourier's law, okay, solve this equation in order to get Qx, so that we can get what is the rate of heat transfer within this boundary. Okay, if this system is under steady state, okay, so you know any point in the system, the Q is constant, it's the same. Okay, I hope try to recall what you have learned in group activity 1-2. To derive equation for temperature profile Tx, then we need to start with energy balance equation, and I think this is not something new to you since you have learned it in the energy balance. So the formula is basically, so if you see the system, okay, if you see the whole system within this Q, okay, energy balance equation says that total heat or total energy going in, okay, from X, from Y, from Z, okay, going into the system, plus energy generated within the system, okay, that is Vg. G is the energy generation rate. V is the volume of the system. Okay, then equals to energy out from X, from Y, and from Z, plus energy consumed within the system. And this formula is V rho Cp delta T over delta T. So V rho actually equals to M, that is the mass. So basically this formula comes from mCp delta T. Just that you need to take note, this is a partial differential equation. Okay, so in order to solve this, it requires longer steps. Okay, and with certain assumptions, so we can simplify the whole energy balance equation. So which you're going to go through this after this. These are the formulas. These are the basic equation for energy balance which you need to start with when deriving equations for different scenarios. So for Cartesian coordinates, so this is the basic equation you need to start with. For cylindrical, so Cartesian example, maybe you have a flat sheet, okay, something like, so you have x, y, z. Then for cylindrical system, you start with this. So cylindrical, for example, you have pipe, right? You have pipe, okay, and heat is, let's say, being transferred from inside to outside through the pipe wall. So this is an example of cylindrical coordinates. And for spherical, then you need to start with this. So spherical, so let's say you have a sphere, have a ball, okay, hollow inside. Okay, so let's say heat inside you have is filled with hot filling. Okay, so heat is being transferred from inside to outside through through the wall. So this is example, okay, of spherical system. Now let's proceed to the first scenario. So these are the conditions. First, one-dimensional X. So what does it mean by that? It means heat, we only consider heat is conducted within this system in one direction, in X direction only. So you can see you have X, you also have Y, you also have Z. So we only under such condition, we only consider heat transferred through the X, in the X direction. So of course we know in actual situation heat also transferred through Y, okay, Y direction, in this direction, and also in Z direction, okay, but Y and Z, heat transferred through Y and Z are not being considered in this derivation. So this is the first thing, so meaning one direction only. Then second is no heat generated, so meaning you can see this is the boundary. Our boundary is from x equals to x1 to x equals to x2. So meaning the generated, the so-called derived equation can only explain the heat transfer rate within this boundary, okay, and heat transfer rate outside this boundary cannot be calculated through the derived equation, okay. And when we say no heat generated, it means within this boundary there is no heat generated within this boundary, okay. Maybe so in actual situation there is no heater within this, okay. So a typical example we maybe suit this this scenario is maybe a wall of a house during winter, okay. Let's say you see so here T1 is higher than T2, so meaning inside the house, the temperature inside the house is higher than outside the house because it's during winter. So we know heat will be lost from the house, from the inner wall to the outer wall. Okay, so when we say no heat generated, meaning there is nothing, there is no heater within this wall. Okay, so that's why there is no heat generation. Okay, and when we say steady state condition, so try to recall what you have learned in the previous lecture. So steady state, when we say steady state, it means the heat transfer rate throughout this, within this boundary, every point the Q is the same. Okay, Q is the same because of this assumption, steady state. Okay, and another important important result of steady state condition is temperature at every point doesn't change over time. When time change, let's say here is T naught. So when time change, this point, the temperature still remain at T naught. Okay, so this is when we say steady state. Again, there is another assumption under this derivation, that is, we assume the cross-sectional area is constant, is uniform, sorry, is uniform. Okay, so where is the cross-sectional area? Here is the cross-sectional area. Okay, so this A. So as you can see, from x1 to x2, okay, so the cross-sectional area is uniform, it doesn't change, so A is a constant. Okay, so and when we derive equation, so boundary condition is important. Okay, I have explained already. So boundary condition is actually our boundary, meaning whatever, so that the equation derived is only applicable within the boundary. So in this case, our boundary condition is from x1 to x2, x1 to x2, and at x1 the temperature is T1, at x2 temperature is at T2. Okay, so these are the background for this scenario. So now, with this assumption and the boundary condition, let's start deriving. So from the Fourier's law, Qx. So first we want to move dx to the left, okay, in order to solve this differential equation. So dx equals to negative ak dt. Okay, then in order to solve this, we need to do integration. So why I put qx outside, because you still remember we are considering the system under steady state. So under steady state, heat transfer rate within the boundary, within the system, is constant. Okay, so that's why it's a constant, so we put it outside. So same goes to A, because we assume constant cross-sectional area. Then K, thermal conductivity, we also assume within the boundary it is also constant. Okay, then let's see. So the boundary here is x1 to x2, and at x1 temperature is T1, at x2 temperature is T2. So it's quite simple, it's quite easy to solve this. So the solution, I believe you see already, x2 minus x1 divided equals to negative AK T2 minus T1. We want to remove this negative, so what we can do is it becomes AK T1 minus T2, and Qx therefore is equals to AK T1 minus T2 divided by x2 minus x1. And if you want to present this equation in the form of driving force divided by resistance, so we can write it like this, because we know temperature difference is the driving force. So here x2 minus x1 divided by AK, so Qx, so this is the driving force, and the below part is the resistance. So this is the equation we derive for heat transfer rate. Okay, and you can see here Qx, the unit is watt, meaning joule per second. So if you put A here, so meaning if Qx over A, okay, then this property, this quantity becomes heat, heat flux. Okay, and the unit is watt per meter square. Let's derive equation, our second equation under scenario number 1, that is for temperature profile Tx. So we need to start from energy balance equation, and since this is a Cartesian coordinate system, so we will start from this basic equation. So you can see it's quite complicated. It's even it's a partial differential equation. Okay, so but with the assumption that we have made, as I mentioned earlier, this very complicated equation can be further simplified. So let's see how it can be simplified. So first, because we assume, so or we would say we only consider the heat transferred in one direction, in x direction. Okay, so the part which involve y and z in the Cartesian coordinate system will be 0. They become 0. Okay, and we also we also know that our system there is no heat generation. Okay, so this part, the heat generation part, will also become 0. Then because of the steady state condition that we are considering, okay, so we know that under steady state condition, temperature at any point doesn't change with time. Okay, since changes of temperature over time is 0, so this part also become 0. So with that, if we move alpha to the right, then it also become 0. So the whole very long equation becomes like this. Okay, delta 2t divided by delta x2 equals to 0, and this is a partial differential equation. So we know under this situation, because temperature only solely depends on x, okay, temperature doesn't depend on time, on any other thing, any other factor anymore. So under such condition, this PDE, partial differential equation, can be further simplified into the ordinary differential equation. So from partial becomes ordinary. So our works is further simplified. So we can start our derivation from this equation. Okay, and now let's start the derivation. Okay, we know d2t over dx2 equals to 0 can also be written in this form. Okay, so in order to solve this, we need to integrate this for 2 times, double integration. Okay, so let's get started. dx dt over dx so equals to 0. Okay, so we know it becomes, after the first integration, it becomes dt over dx equals to c1. Okay, here you integrate 0, you get a constant. Okay, then we integrate for the second time. Okay, so we move the dx to the right side. Okay, integrate, so we get tx equals to c1x plus another constant c2. Okay, so now after 2 times of integration, we get the temperature profile, but our equation contains 2 constants, c1 and c2. Okay, so we need to solve for c1 and c2. Okay, so how to solve? Solving for c1 and c2 using the boundary conditions we assumed earlier. Okay, so our equation is tx equals to c1x plus c2. So with the first boundary condition, we know that t1 equals to c1x1 plus c2, equation 1. Okay, because according to our boundary condition, at x1 temperature is T1. Okay, so similarly for point number 2, it becomes like this. So T2 equals to C1 x2 plus C2. So we can solve this simultaneously. Okay, 2 minus 1. Okay, when we do this, then we'll be able to remove the C2. So it becomes T2 minus T1 equals to C1. We factorize it, x2 minus x1. Okay, and we get C1 equals to x2 minus x1 divided by T2 minus T1. Okay, next let's solve for C2. How we can solve for C2? Okay, so just substitute C1 into equation 1. Substitute C1 into equation 1. So we get T1 equals to x2 minus x1 over T2 minus T1 times x1 plus C2. And with this we get C2 equals to T1 minus T2 minus T1 divided by x2 minus x1 times x1. Okay, so now we can substitute the C1 and C2 into this equation. So Tx equals to, so C1 equals to T2 minus T1 divided by x2 minus x1 x, okay, because here is x, then plus T1 because C2 equals to T1 minus T2 minus T1 divided by x2 minus x1 then x1. Okay, then let's factorize it so that it looks shorter. So at the end we get Tx equals to T1, we move it to the front, then we can factorize it, plus x minus x1 times T2 minus T1 divided by x2 minus x1. Okay, so this is the equation for temperature profile within the boundary condition, meaning by using this formula we'll be able to know, okay, so within these 2 points, so this is x1, this is x2, so and here this T1, this T2. So and the profile should be like this, because you know it's in the form of y equals to mx plus c. So you see the here is T1. Okay, so it's a linear, meaning the temperature profile is linear. Temperature changes linearly from x1 to x2. Okay, and with this formula, when we know the x, okay, we can know the temperature at that point. Okay, if T1 and T2 are known, then if we know the location, okay, we'll be able to calculate, to identify the temperature at any point within this boundary by using this formula. Okay, and now let's proceed to the second scenario for derivation. So as you can see, it is quite similar to that of scenario number 1. So we also only consider heat transfer in one direction. Okay, in our case is x direction. Okay, but you can see now is the difference is we are taking the center of the object as x equals to 0. Okay, so in scenario number 1, our x equals to 0 is here. Okay, this is scenario number 1. But in scenario number 2, as you can see here, the x equals to 0 is at the center. Okay, is at the center. Okay, then we also consider assume the system is under steady state. Okay, then now there is one additional condition, that is with heat generation. Okay, what does it mean? So if you see the center of this object, so you can see the color shows that the temperature here at the center is the highest. Okay, why it is highest? Okay, because there is some heating. Okay, there is constant heat generation take place in this part. Okay, so in actual you might wonder, in actual situation, could this be possible? So it is possible. In actual situation, the situation could be maybe this is some kind of storage. Okay, some kind of storage. For example, let's take this one, some kind of storage. So in the center, so let's say this is actually hollow. Okay, hollow. Okay, so you store something here. Okay, maybe there is radioactive. Okay, radioactive components inside. So these radioactive components are releasing heat, constant heat, generating heat. Okay, or it could be like there is some sort of heating element in the center. Okay, keep releasing, keep generating certain amount of heat, and this heat is being released, okay, to the surrounding through the walls. Yeah, so this is the situation. Okay, and as you can see here, the heat is generated at this rate. Okay, heat generation rate is G. Then the unit of heat generation rate is watt per meter cube, or joule per second per meter cube. Okay, so meaning heat generated, heat released per unit volume. Okay, then another thing you see that is different from scenario 1 is you can see the whole object is being divided. Okay, let the whole length, okay, the whole length, let's say from x equals to 0 to x, so the whole length is named as 2L. Okay, so since our 0 start at the center, so you will see x equals to 0 is at the center of the object. Then because the whole object is divided by 2, so the whole length is 2L, so that's why from the center to the wall the distance is L. From the center to another side of the wall the length is also L. Okay, so you might ask why. Okay, this is for the ease of derivation. Okay, for easier for us to derive. You will see this later. Okay, so and another thing another assumption is we assume the object has uniform cross-sectional area. So you can see now we have two objects here. Okay, 1 and 2. So object 1, the cross-sectional area is rectangle. Okay, it's like this, and you can see when x change, a remain constant. Okay, a remain constant. Same goes to this cylindrical object. So since heating element is at the center, so here would be x equals to 0. Then here would be L, because the whole thickness of the cylinder is 2L. So from the center to one side is L, from the center to another side is also L. Okay, so and you can see the cross-sectional area when x change remain the same, remain constant. Okay, so these two objects fulfills all the assumption and all the condition for derivation. Okay, another thing I need to mention here is because of our assumption of steady state, then we can also assume that the heat transfer rate in any point, okay, within these objects, okay, because of steady state, so Q within this object at any point will be constant. Okay, so with this in mind, we will start the derivation. Okay, now let's start the derivation. So we will, for scenario number 2, we will start deriving from for Tx, that is temperature profile. Okay, different from scenario what we did for scenario number 1, where we start from Qx, the heat transfer rate. We started from Fourier's law. Okay, why we start from Tx? Because along the way, one of the equation we derive will be used for the Qx derivation. So that's why we need to start from Tx first, specifically for scenario number 2. Okay, and let's see. So we know already to for Tx derivation, we will start from energy balance equation. So this is the equation, and because of our assumption, heat is we only consider heat transfer in one direction, that is in x direction. So that's why for y and z becomes 0, and because of another assumption, that is we consider the system in steady state. So that's why this part delta T over time, change of temperature over time, also becomes 0. And for scenario number 2, G, heat generation rate, is no longer 0, so that's why it remains. Okay, then there is another term here. We see alpha. So alpha equals to K over rho Cp. So alpha, for your information, is a term called thermal diffusivity. Thermal diffusivity. Okay, so K is thermal conductivity, rho is density, Cp is heat capacity. Okay, so we change alpha to K over rho Cp. Okay, and this is what is remain. Then we move this part to the right. Okay, rearrange everything. Then we can cancel out rho Cp. So at the end, this is what we obtain. Okay, alpha 2t over alpha x2 equals to negative g over k. And I have mentioned already for scenario 1, this is the same, because under this kind of situation, temperature only solely depends on distance, location, x. So that's why the partial differential equation can now be simplified to ordinary differential equation. So that's why the partial part now become d2x over dx2. So our derivation will start from this simplified equation after considering all the assumptions. Okay, let's start our derivation from introducing the boundary condition first. So consider this system. I've explained about this. So let's see the boundary conditions. Okay, we are considering from x equals to 0 to x equals to L. Okay, so x equals to 0 is at the center. Then we know that the temperature here is the highest. Why? Because here is where there is the source of heat generation. So logically we know that here should be the point where we have the maximum temperature of the whole system. Okay, then when x equals to L, then the temperature is T1. Okay, when x equals to 0, the temperature is T naught. Okay, and we know T naught is the maximum temperature of the system. Okay, let's see. So boundary condition 1 is when x equals to 0. Then okay, this one you learned already in calculus. So we know for the Cartesian system, so when we differentiate dy equals to dx, so at maximum or minimum point of a curve, then dy per dx equals to 0. So same goes to this. Okay, we know that the function of temperature change like this. Okay, so at here, at the maximum point, where we have maximum temperature, dt over dx equals to 0. Okay, so this is our boundary condition 1. Then boundary condition 2 is similar to our scenario 1, that is when x equals to L. Okay, at this point, then t equals to T1. Okay, let's get started. So d2t over dx2 equals to negative g over k. So we write transform in this form. Okay, then integrate for the first time. So since it's a double differentiation, so we need to integrate for 2 times. So we integrate for the first time. This is what we get. dt over dx equals to negative g over k x plus, there is a constant. So let's term this as equation 1. Okay, then let's integrate for the second time. Okay, when we integrate both sides for the second time, so this is what we get dx equals to negative g over, so here we have x already, so it's x2, then here we have 2k plus c1x plus another constant, let's term it as c2. So let's term this equation as equation number 2. Okay, and we need to solve for the 2 constants c1 and c2. So let's start from solving for c1. Okay, in order to solve for c1, we need to refer to equation 1. Okay, and boundary condition 1. Okay, so equation 1, dt over dx equals to negative g over k x plus c1. Okay, so when we consider boundary condition number 1, we know that at this condition dt over dx equal to 0 because the temperature is maximum at this point. Then g over k and x equals to 0 plus c1. So from here we know that c1 equals to 0. Okay, solve for c1. Then now let's solve for c2. c2 will refer to equation number 2, boundary condition number 2. So tx equals to negative g over 2k x2 plus c1 is 0, so this part can be removed, so c2. Okay, we substitute boundary condition number 2 here, so tx, so here it becomes t1. Okay, negative g over 2k x equals to L, C2 plus C2. So we can solve for C2 because C2 now equals to T1 plus G over 2K L square. Okay, so now we have solved for both C1 and C2. Let's substitute the two values into equation number 2. Okay, substitute C1 and C2 into equation number 2. So this is what we get Tx equals to negative G over 2k x square, so C1 equals to 0, then plus C2 equals to T1 plus G over 2k L square, then Tx, so let's do some factorization. Then we get Tx equals to G over 2k L square minus x2 plus T1. Okay, so we have done with temperature profile. Now let's continue with the derivation of Qx. Okay, start from Fourier's law. So we know Fourier's law stated Q equals to negative AK dt over dx. Okay, integrate both sides. Okay, when we integrate, okay, we move dx to the left, equals to negative AK dt at the right. Integrate both sides. So let's take boundary condition here from 0 to L. Okay, we are considering from 0 to L because we want to know the heat transfer rate from here to the right, okay, to the surface. So from 0 to L, then when x equals 0, temperature is T0. When x equals to L, temperature is T1. So we integrate both sides. This is what we get. Q L minus 0 equals to negative AK T1 minus T0. Okay, and we get Q x equals to AK. Okay, after you arrange everything, yeah, we want to get rid of negative side, so we change the position between these two, T0 minus T1. Okay, you can even continue to make it in the form of like this, T0 minus T1 divided by AK over L, so that it becomes driving force divided by resistance. Okay, done.